Okay, let's take a look at the next part of our lesson on factoring quadratics of special cases. So this time we're going to factor what's called a difference of two squares in the form of a squared minus b squared. And it's just undoing the product of conjugate pairs. So factoring the difference, so difference means subtract, two squares means my first and second terms are both perfect squares. And let's talk about what conjugate pairs. Conjugate pairs are binomials with the same terms, but they have opposite operations. And you can see here three different examples. So when we multiply conjugate pairs, let's see what happens. And now I'm going to multiply by the -2. So you can see these middle terms, these linear terms are going to cancel or add up to 0. So my A value is 1, my B value is 0. Okay, so let's remember our standard form of quadratic trinomials. So my A is 1, my B is 0, and my C is -4. So this is what we will call the difference of two squares. Okay, now let's multiply x plus 4 times x minus 4. And again, we're going to see our two middle terms are opposite, so they are going to cancel out. So this is a difference of two squares. And our last example here. So we have a perfect squared minus a perfect squared. So if we can recognize the difference of two squares, then we're going to be able to use our shortcut of factoring. So remember, when we have the difference of two squares, this is what the two factors are going to look like. They're going to look the same with opposite operations. And these are called conjugate pairs. So now there is no such thing as a quick formula for factoring the sum of two squares. It has to be the difference. So here we have x squared minus 81. We don't have the linear term. We have subtraction. X squared is a perfect squared and 81 is a perfect square. So you set up your two factors. These are going to be conjugate pairs. So we're going to factor x squared into x and x. We're going to factor 81 into 9 and 9. One needs to be plus and one needs to be subtract in order for the middle term to become 0. So here are the two factors, and you could write these in the opposite order. Again, if you did not recognize that this is an easy quadratic to factor, that it's the difference of two squares, if you did not recognize, we can always go back to grouping and using the big X to find our factors. Okay, here's our next example. I see that our A value is not 1, so I know that they're both even numbers, so there is a GCF. And because I am very familiar with my perfect squares, I recognize that 225 is a perfect square. We have subtraction for our difference and our two perfect squares, x squared and 225. So I'm going to bring down the GCF. I'm going to set up for the conjugate pairs. I'm going to take the root of each one of these perfect squares. One needs to be subtract and one needs to be addition. Here are the three factors of this quadratic. X squared minus 196. We have the difference of two squares, x squared and 196. I do not have a linear term. So we're going to set up. We're going to take the root of each term. Again, I'm familiar with my perfect squares, so this makes it very easy for me to do. So if you don't know your perfect squares all the way through 20, like 20 squared is 400, being familiar with your perfect squares is going to be very helpful. Okay, 9x squared minus 144. So let's see if 9 can go into 144. These are both perfect squares, so if I didn't recognize that there's a GCF, let's see what happens. So I take the square root of 9x squared, break it down into the two factors, and then we have 12, one's plus and one's minus. But here's what I noticed. 3 can be factored from all of these. So we did have a GCF. So I'm going to factor out 3 and 3. And so really we could have originally divided to see if 144 is divisible by 9. Oops, that's a 1. 1 times 9 is 9. And then 54, and that is 16. So yes, these were divisible both by 9, giving us x squared minus 16. And see, I can see 16 is a perfect square, but let's say we did not see that. We would factor out a 3 from this binomial and a 3 from this binomial. So that gives us a 9, and we would be left with x plus 4 and x minus 4. Okay, but we should have checked to see if 9 could divide it into 144, and it did. So again, that would give us this, and this binomial is the difference of two squares. So x and x plus minus 4 and 4. So whenever we factored here, if we would have left it like this, we would have not got full credit because they're always going to ask you to factor it completely. And I have a 3 embedded here and a 3 embedded here. So if I pull both of these 3's out, that's where we get the 9 here. Okay, our last one. Let's see. The square root of 361 is 19. That's prime. So I don't think there's a GCF. So this is a difference of two squares. So when I break it down, I can tell if there was a GCF. And that's going to give me 19 and 19. And I can see there's no GCF of 4 and 19. So here is our final answer. And again, if you don't recognize the difference of two squares, you can always use the grouping method. Now be careful, and I want to just show this problem. If I have 16x squared minus, let's say, 361x, this is not the difference of two squares, because this x is not a perfect square. It's x to the first. So this is not the difference of two squares, but there is a GCF. I could factor out a 16 from each of these. And this would be my two factors, x and 16x minus 361. So just make sure that you recognize the difference of two squares means both terms are perfect squares. 361x is not